You've probably used models like ChatGPT or Claude. You give them an instruction, they follow it. This feels natural, almost like you're talking to a person. But I'm here to tell you, it's a carefully engineered illusion. The underlying base model, the one that's fresh from its training, is not an assistant. Not at all. It's a powerful, almost alien-like text completion engine. It has one and only one goal: to predict the next word in a sequence. That's it. Nothing more. This singular, obsessive focus creates a big problem. A problem I call the Parrot Problem. The model becomes a master of mimicry. It can copy patterns perfectly, but without any concept of what you actually want. It doesn't understand you. Let's make this crystal clear. Imagine you have a raw, pre-trained LLM. You ask it a simple question. The prompt is, what is the primary cause of Earth's seasons? Now, what do you expect? An assistant would give you a helpful, clear response. Something like, the primary cause of Earth's seasons is the tilt of the Earth's axis, which is about 23.5 degrees. Simple, direct, helpful. But that's not what the base model gives you. Look at this. The base model is much more likely to respond with this. What is the primary cause of Earth's seasons? A, the Earth's distance from the Sun. B, the tilt of the Earth's axis. C, the speed of the Earth's rotation. It didn't answer your question. It turned it into a quiz.
What? Why? Why would it do that?
Because in its training data, it saw a pattern. It learned that questions phrased like, what is the primary cause of, are very, very often followed by a multiple choice format on the internet. The model isn't being unhelpful on purpose. It is perfectly executing its one and only objective, completing a pattern. It has no concept of a user or an instruction. It only sees text, and it completes the most statistically likely pattern. This gap, the massive chasm from a pattern-matching parrot to a helpful assistant, is closed by a process called supervised fine-tuning, or SFT for short. Now, that sounds complex, I know. But here's the secret. The entire challenge, the whole engineering problem, boils down to one single function. And here's my promise to you. In the next 30 minutes, not days, not weeks, you will write this exact function from scratch.
Okay, let's look at the core logic of SFT.
Don't be intimidated by the code on the screen. By the end of this video, you'll understand every line. First, let me show you the big picture. This is the full script for supervised fine-tuning. It's called Prepare SFT Batch, and it does something brilliantly simple. Here's the most important line in the entire function. This is it. This is the entire trick. By setting the prompt labels to -100, we tell the model's loss function to completely ignore the user's prompt during training. We force it to learn one thing and one thing only. When you see this pattern, your job is to generate the expert response. Mastering this one function is mastering SFT. So here's our journey. If you look at this diagram, you'll see it all laid out. We start with the pre-trained LLM, which has the objective of next token prediction. This leads to the Parrot Problem. The solution, imitating expert examples using this loss masking technique we just built. That's supervised fine-tuning. And the final result is a helpful, instruction-following, aligned assistant model. All right, let's pull back the curtain and look at the engine that powers these incredible models. A base LLM's vast knowledge is forged during pre-training. It spends weeks, sometimes months, learning from trillions of words. But here's the amazing part. It's all based on a single, brutally simple objective. And that objective is next token prediction. The rule is incredibly straightforward. Given a sequence of text, Your only job is to predict the very next token. That's it. Seriously. The entire foundation is built on being a highly sophisticated pattern completion machine. So, how do we teach it this skill? We use the standard workhorse of deep learning, cross-entropy loss. I know, that sounds super intimidating, but stick with me. It's actually a very simple idea. It's just a way to measure how surprised a model is by the correct answer. Think of it like this. When the model is not very surprised, we call that low surprise. It means the model assigned a high probability to the correct token. And because it was confident and correct, it gets a low loss score. Good job, model. But what if the model is very surprised? We call that high surprise. This happens when the model assigns a very low probability to the token that was actually correct. In that case, we give it a high loss score. Bad job, model. Try again. Mathematically, this all simplifies down to a beautiful little formula. The negative log probability of the correct token. To make this crystal clear, let's tackle a problem and calculate the loss for one example completely by hand. Imagine we have a tiny vocabulary, just 6 words. Pad, the, cat, sat, on, and mat. Our input sequence is the cat sat, which corresponds to the token IDs 1, 2, 3. The target sequence, what should come next, is cat sat on, or token IDs 2, 3, 4. Okay, the model processes the input and produces these raw scores, which we call logits. You can think of logits as the model's raw, unnormalized confidence scores for what the next word could be. Check out this table. For each position, it gives a list of scores. After the word the, you can see the model gave a score of 2.0 to the token for cat. Seems pretty confident. To get our final loss from these logits, we just follow 3 simple steps for each position in the sequence. First, softmax. This is a function that just cleans up the raw logits and converts them into a nice, clean probability distribution where all the values add up to 1. Second, get target probability. We just look at that list of probabilities and we pick out the one probability the model assigned to the correct token. And third, calculate loss. We take the negative log of that single probability. That's it. That's our loss for that one step. Okay, let's walk through the math step by step. I want you to see exactly how this works. Look at the table with me.
We'll start with step 1. The input context is just the word the. The correct next token, our target, is cat, which is at index 2. Now look at the model's logits. See that high score? 2.0. That's the logit for cat. When we run that whole vector through the softmax function, it becomes a probability of 0.593. So the model is about 59% sure the next word is cat. To get the loss, we take the negative log of that number, and we get 0.522. First step, done. Now for step 2. The input context is the cat. The target token we want is sat at index 3. The process is identical. The model's highest logit is 2.5. After softmax, that becomes a very confident probability of 0.793. The model was even more sure this time. So the loss, the negative log, is lower, just 0.232. Okay, last one. Step 3. The context is the cat sat, and the target is on. The model gives its highest logit yet, 3.0. After softmax, that's a probability of 0.773, which gives us a loss of 0.257. Great, we have 3 separate loss values. To get the final loss for the entire sequence, we just take the average of those three numbers. And the total loss is 0.337. Now here's the magic. In PyTorch, this entire multi-step process we just did by hand is handled by one single function.
Let's prove it. Don't get scared by the code, we'll walk through it. What's important is that these are the exact same numbers from our table. We define our logistical tensor, which has our 3 sets of scores, and we define our targets tensor, which has the correct answers, 2, 3, 4. The next 2 lines just flatten the tensors, which is just a little reshaping that PyTorch needs. And then we call the magic function, f.crossentropy, passing in our logits and targets. And the output? Look at that. The calculated loss is 0.337. 0.337. It perfectly matches our manual calculation. This is the simple, powerful engine that drives large-scale pre-training. Now we can see the source of the Parrot problem with perfect mathematical clarity. The model's sole objective, its only goal in its entire existence, is to minimize this cross-entropy loss. It will do whatever it takes, twist its internal weights in any way it can to reduce its surprise. So let's revisit that prompt. When you ask it what is the primary cause of Earth's seasons, it's not trying to be helpful. It's not trying to access knowledge. It's asking itself a very different question. It's asking, across the trillions of tokens I have seen, what tokens are most likely to follow this sequence to give me the lowest possible loss? And since its training data is absolutely full of quizzes formatted like Q:something, A:something, well, completing that pattern is the path of least surprise. It's the statistically easiest way to get a low loss score. The model is a parrot because its training objective is mimicry.
To fix this, we don't change the engine.
We change the fuel. This is the core idea of supervised fine-tuning, or SFT for short. And it's beautifully simple. If you want a model that follows instructions, you must show it a large, high-quality dataset of instructions being followed correctly. Think of it like this. Pre-training is like locking the model in a library with every book ever written and telling it to learn the patterns of language. Supervised fine-tuning, on the other hand, is like taking that model out of the library and handing it curated, expert-written flashcards. Here's the difference. Pre-training data is unstructured web text. It's massive, it's noisy, it's unfiltered. And its goal is just to mimic patterns. SFT data is structured. It's made of prompt and response pairs. It's small, clean, and very high quality. And its goal is to imitate expert behavior. Each flashcard is a high-quality prompt and response pair. For example, the prompt might be, explain the concept of gravity to a 6-year-old in a short paragraph. And the expert response would be, imagine the Earth is a giant magnet, but for everything. It's always gently pulling you and your toys down. That's why when you jump, you always come back down. This special pulling power is called gravity. But we can't just feed these in separately. An LLM only understands a single continuous sequence of tokens. More importantly, it needs to learn the structure of a conversation. To solve this, we introduce 2 key tools, special tokens and a chat template. We format the data like this. We start with a special token, user token. Then we insert the prompt. Then we have an in token. Then we have the assistant's special token, and finally the expert response, followed by another in token. This teaches the model the turn-taking rhythm of a conversation. So for our gravity example, it all becomes one long string. User,
Explain the concept of gravity. Assistant, imagine the Earth is a giant magnet. But now, we face a critical problem. If we train on this entire sequence, we would be training the model to predict the user's prompt as much as the assistant's response. This is completely wrong. We only want to penalize the model for mistakes it makes when it's the assistant's turn to speak. The solution is an elegant engineering trick called loss masking. Here's the aha moment. It's so clever. We create our input ID's tensor with the full conversation just like we saw. Then we create a second tensor called labels. For every token we want the loss function to ignore, we replace its ID with a special value, -100. Why -100? Because PyTorch's cross-entropy loss function is hard-coded to completely ignore any target with this value. It's a built-in skip instruction.
Let's see loss masking in action. We're going to walk through this entire process together step by step. Simple tokenization. User equals 6, explain equals 7, gravity equals 8, end equals 9, assistant equals 10, gravity equals 11, is equals 12, A equals 13, force equals 14. Check out this table. Input IDs contain the full conversation, but labels are masked. First token, user. Input ID is 6. Label, -100. Loss calculated, in O. Next token, explain. Input ID 7. Label, -100. Loss calculated, no. Now, I'm not going to repeat the details, but here's the pattern. Gravity, end token, assistant token, all get input IDs but labels of -100. No loss calculated for any user prompt tokens. But now, look what happens with the assistant response.
First response token, gravity.
Input ID 11, label also 11. Loss calculated? Yes. The rest follow the same pattern. Is a force end token? All have matching input IDs and labels. All calculate loss. This achieves our goal perfectly. The model sees the full context, but the gradients, the learning signals, are only calculated on its ability to generate the expert response. It learns the one critical rule. When you see user token until assistant token, your goal is to generate the following sequence. This is what turns the parrot into an apprentice assistant. This entire process can be summarized with a formal mathematical objective. Now, I know it looks a bit scary, but it's just a precise way of describing the table we just made. All this says is, we minimize the average negative log probability, but the summation part, that happens only over the tokens in the target response Y, not the prompt X. That's it. That's the formal math behind our simple loss masking trick. We now have the complete theory of supervised fine-tuning. We know why we need chat templates, and most importantly, we understand the critical role of loss masking.
Time to implement. Let's get our hands dirty and build the prepare SFT batch function. Now, here's a little secret. The main engineering task in SFT isn't the training loop itself. That's pretty standard stuff. The real craft is in the data collation. To keep our focus laser sharp on the logic, we're going to use a minimal towering and a really simple batch of data. No complex libraries, no distractions. Just the pure mechanism. Look at this setup code. First, we're importing torch. Then, we define a simple Toganosaurus class. Seriously, there's no magic here. It's just a Python dictionary mapping words to numbers. We have our vocabulary with things like pad, the, quick, brown, and of course our special tokens, user, assistant, and end. We instantiate that tokenizer, and finally, we create a sample batch of data. Just 2 examples. The first prompt is the quick brown fox. and its response is jumps over the lazy dog. The second is what is a dog, with the response a lazy brown fox. Simple, right? Okay, with our setup ready, now let's build the SFT data collator. This is the heart of the operation. We're going to walk through this function together, step by step. It takes our batch and our tocation and does all the magic we just discussed. First up, step 1. Format with the chat template. We loop through each example in the batch.
We create the prompt part by adding our special tokens like user tokens
and assistant tokens. Then we create the full text by tacking on the response and the final end token. Easy enough. Next, step 2. Find the masking boundary. This is critical. We tokenize only the prompt part. Why? Because the length of these tokens tells us exactly where the assistant's response begins. We store this length in a variable called maskUntilIndex. Now for step 3. Tokenize the full text for input. This time, we encode the entire full text string. This will be the input IDs that the model actually sees. It needs the full context, remember? Okay, moving on to step 4. Create labels from inputs. This is a neat trick. We just clone the input yield tensor we just made. Right now, the inputs and the labels are identical, but not for long. Because now, step 5, apply the mask. This is the core SFT trick. It's so simple, but so powerful. We take our labels tensor, and for every token from the beginning up to our maskUntilIndex, we set its value to -100. And that's it. We append our finished input underscores IDs and labels to our lists, and then stack them into tensors at the end. Now let's process our batch and see the actual tensors. We'll run our little SFT underscore batch through our new SFT underscore data collator function. And here's the output. Check it out. Under prepared batch, you can see the input IDs tensor. It's just a sequence of numbers. But look at the labels tensor right below it. See all those -100s at the beginning? That's our mask. Then, when we decode only the part of the labels that isn't -100, what do we get? We get jumps over the lazy dog. Perfect.
The mask is working perfectly. The input IDs see the full context, but the labels ensure the model learns from the expert response only. And because we did all that hard work preparing the data, the training step is now trivial. Any standard transformer model using cross-entropy loss will automatically handle that -100 masking for us. Look at this conceptual training step function. We put the model in train mode, zero the gradients, and then we just pass our batch of input IDs and labels straight to the model. The model's forward pass calculates the loss, magically ignoring all the -100 labels. Then we just call loss.backward and optimizer.step. Done. And that's it. We have successfully implemented the full SFT pipeline from scratch. The Parrot is learning to become an assistant, but this powerful method of direct imitation has a crucial weakness. It treats all good responses as equally good. We've taught the model what to say, but not how to judge. We've done it. We've completed the journey. We have gone from a useless parrot to a functional assistant. It's an incredible transformation. So let's take a moment to recap exactly what SFT actually achieved. First, it now understands structure. It finally recognizes the roles of user tokens and assistant tokens. It knows its place in the conversation. Second, it adopts a persona. It is learned to imitate the style and the helpful tone of your expert data. And third, and most importantly, it follows instructions. It can reliably perform the tasks that were covered in its training. You have successfully built an apprentice assistant. It's learned the rules. It can replicate the examples it was shown. SFT is the bedrock. It's the foundation upon which all modern alignment is built. However, SFT has a profound, built-in limitation. It's a subtle but critical weakness. SFT treats all good answers as equally and perfectly good. It doesn't understand nuance. Let me make this concrete for you. Imagine a user asks, "Summarize the impact of the printing press." Now, in your expert data, you have two possible answers.
Response A, which is a good response, says, "The printing press allowed mass production of books, making information more accessible." Okay, not bad, factually correct. But then there's response B, a better response. It says, "The printing press democratized knowledge, fueling the Renaissance and scientific revolution by enabling the rapid spread of ideas." Now, as humans, we can immediately tell response B is better. It's more insightful. It provides deeper context. It's just a higher quality answer. An SFT model cannot learn this relative preference. If you only show it answers like A, it'll be basic. If you show it A and B, it will just learn to produce an average of the two. It has no way to know that B is more desirable than A. You see, SFT teaches a model what to say, but not how to judge or how to choose. To overcome this, we must move beyond simple imitation. This is where we need preference tuning. Now, preference tuning requires a totally new kind of dataset. It's not just a prompt and a response anymore. It's a triplet of a prompt, a chosen response, and a rejected response. Look at this diagram here. It's pretty simple. We show the model a prompt, then we show it two options. We explicitly tell it this is the chosen response with the green check mark, and this is the rejected response with the red X. We're literally teaching it our preferences. So the goal of preference tuning is this. For all the chosen responses, we teach the model to assign a higher probability to that sequence of words. And for all the rejected responses, we teach the model to assign a lower probability to that sequence. This is exactly what advanced algorithms like DPO and RLHF do. So you see, SFT is not the end of the alignment story. Not at all. It is the essential first chapter. SFT is what transforms that raw, chaotic base model into something coherent and controllable. It creates the perfect starting point for all that sophisticated preference tuning that comes next. You now understand the fundamental technique, the one that turns a parrot into an assistant. You've mastered the theory, you've mastered the math, you've mastered the code. The entire landscape of LLM alignment starts right here.